Hello. Yes, I am Hubert Mohr-Daurat, lead animation programmer at Creative Assembly. I have been working now for a while as a gameplay and animation programmer.
Your screen.
Oh, yes. So, yes, thank you. And yeah, so I have been working for 6 years in South Korea, working on an MMORPG game called Civilization Online, and later I joined Creative Assembly to work on the animation technology for the Untitled project. I would like to talk to you about the regression test that we have implemented for the character animation system for all the Untitled projects. So first, a bit more about the Untitled series. There are a lot that have been said before about it, but I wanted to say that most of projects have been related to historical contents, and in the recent year there have been also some exploration with the fantasy settings for the Total War Warhammer series. And yeah. So why I wanted to talk about the regression test? It is because those, after 10 years I've been working in the game industry, there was some common problem that often happened, which was that when we are changing the code, when we are making code, it's affecting the content that already exists during development. And this is particularly true for animation, when we are doing animation work, because most of the content is data-driven by animators. And this is even more true for a game like the game we are making in the Total War series, because we have really huge content for the animation. For one project, we have hundreds of characters and thousands of animations just at release. And then we are releasing later additional content with more animation content and also more features to implement in the code. So that's really critical to be able to tackle this issue. So a bit more context about the animation work we're doing. Us, as animation programmer, we are working on the animation technology. We are creating these animation features into the animation code. And in the meantime, there are animators who are making the animation content. So yes, of course, they are making the animation data, the animation itself. But they are also using the animation features that we are creating to combine them in different ways, depending on the need for each character on each animation. And I wanted to show you some example of the kind of animation feature we have in our engine. So this is just some example of them. One of the most simple one is the transition, which is simply how the animation is modified to switch bit from a previous animation on the next animation to make sure to blend it smoothly. We have also all different kind of splicing feature, which is used for applying a different animation for a different part of the body in different way depending on the needs. And there are also more complex type of animation features, such as look cat, sometimes called look IK, which is for modifying the rotation of the head, neck, and spine to make the character look at a specific position. And animators request us to create this animation feature when they need it. And when we add the feature into the animation code, we are adding bugs as well. That's the way it works. When we are modifying code, there is always a risk. Always a risk to add the bugs, to make a change that is not desired. So usually the process will be to us as an animation programmer creating a new feature, we need to change the code for that. And later on, sometimes quite later, somebody from the QA team or animators will find a bug and will ask us to fix it. But to fix this bug, we need to modify this code, to modify the code again. And maybe there was a very specific way that one animator was using this new feature for just one specific character. Maybe one character riding a horse where it needed to be in a different way to be able to attach him right on the horse. And with this second code change, it will fail, and maybe the rider will be on the ground instead of being on the horse. But the problem is we will not find this problem right after. We will find it much later because this is only a very specific case that until somebody encounter it from the QA team or animators, we will not know that we have this bug. So this process is very long, lots of iterations, and not always efficient. So we need solution for that. If we look around, what a common solution in the software development will be to use a regression test. So briefly, what is a regression test? We create a list of tests, which are all different cases that we want to different case for the data that we want to run with the code, and each test will give a specific result. Then later, when we modify the code and make a new version of this code, we can run this test again, and we can compare each test. If there is any difference, it means that we have done a change that is not necessarily desired and likely to be a bug. So that's not specific for animation, that's just something very general. And now the question is how we can apply the same system into animations. So that's something I've been trying to figure out, that I've been trying to figure out for a while. And a while ago, I listened to this talk from Dr. Erik Anderson from Bournemouth University, which was about research he has done together with George Merges and Idris Mice, which is a set of tools, visualization tools, which allow to compare two versions of an animation. So it was supposed to be used for revision control, where when animators create a new version of one animation, it will be possible to see more clearly if there is a change and what change, which part of the body will have changed. So it's not really the same as what we need for the regression test, but that's a big part of it. If we are able to have these tools to be able to visualize it, then it will be really straightforward to actually apply regression test for that. So yes, that's a very simple way that we can do. Instead of using this list of tests, which just return a simple value, what we are doing is all our tests are testing a specific set of specific case of animation data running through a specific combination of animation features. And the result of the test is the pose which is generated by the animation system. So we can have, like that, all different cases for each test, and generate it and save it. And later, when we make a new version of the animation code, we can run the same tests, and we can use this kind of visualization tool that we saw before, that I was mentioning before, which will allow to check if something changed, and also to compare precisely all the position and rotation of the joint to actually know which part exactly changed, so we can see if we have a bug or not, and what exactly is the bug. So is that all? Is it all what we need for to be able to apply our regression test? There is still one problem. there are so many ways that animator combine animation features. It will be too much data to test. There will be thousands of tests to run to be able to make sure that we are testing everything. And also, if our tests are using the animation data that we are also that animators are modifying in production, if when we run the test we see a difference, we are not even sure if this is a change coming from a bug in the code or if it's because animators change one of the animation data. So what we need is to extract a specific subset of data to test, extract it from the production data, and keep it independently. And it should be a much smaller subset. But in that case, if we have this small subset independently from the production data, how can we be sure that our tests are actually testing all the combination of features that we are currently using in production by animators? So the solution will be to use animation feature tagging. I'm sorry for the slide doesn't show very well on this computer, but yeah, basically, so that's the example of animation feature I was showing before. And for each of those animation features, we can assign a tag, which is just a kind of a symbol that is unique for those features. And from that, what we can do is to mark in the code at the place where the feature is implemented, we can add some C preprocessor code to mark the code. This way, later when we are running running the code, we will be able to go through this when we go through a specific path, because it's generating a path for a specific combination of animation features. When it encounters each tag, it will be added into one ID, either by concatenation or sometimes by more complex function composition. But it will give at the end a chain of character, which is a unique ID, an ID which represents the unique combination of animation features that we are generating. So we will be able, once we have that, we'll be able to use it to make sure that, to check if our test, which combination we are actually testing. So what will be the steps to create this test? First, we create an initial set of tests. At this point, we just create it manually, roughly trying to cover all the combination of features that we currently use in production. So it doesn't need to be perfect at this point, but it should be just large enough to cover what we have. And then the second step is to generate those unique IDs, those unique combination of features. So here you can see on the right that's a list of this unique ID that will be generated for one test. So we know exactly all the combination features that we test for this specific test. And if we generate this for every test, and we also generate it when we run the game, we can compare it and making sure that all the tests that we have actually, all the combination features that we have in the game actually are covered by at least one test. And then we can iterate on this list of tests to adjust it depending what we found with the tags. So if one combination of feature, one ID is missing from the test, then we can add one to make sure to handle it. If we see that two tests are testing the same combination features, then we can remove one because it will be redundant. This way we can iterate until we get a much smaller set of tests, and we are sure that we are testing everything that we have in game. And also later, if one animator is using a different way one combination of features, then it will warn us because we can assert on this. We can compare the lists as well in runtime, and we will be able to update our list of tests and to add the tests that are missing. So we can always keep it up to date. So now I want to show you one example of how we implement it in Total War 3 Kingdoms. So the initial list of tests was around 2,000 test cases, which is way too much. It will take 10 hours to run the regression. That's not really reasonable. And also, at that point, we just make it manually, so we don't know if we cover everything. Then we go through the method I explained before to check with the tags, and we ended up with only 200 test cases around, which now will take only 1 hour to run the regression, so it's more reasonable timing. And most importantly, we guarantee to cover all the cases that we have in production. Now, we have our list of tests. The important thing is, what can we do with it? So now what we want is to run this, to do the comparison for the pause, to check if there is a difference between the previous version and the next version. For that, that's very straightforward. This is just comparing the pause, the local translation, and the local rotation of every joint of the character for the generated poses for every frames during the test. We need to use tolerance on the distance and angle just because of floating point precision. It might cause some false positive. So that's important thing. But then the next step, we not only want to know, at that point we're able to check the result of the test, to know if one test failed. But what we want is to be able to precisely check which part of the body has been affected, what exactly changed, and to decide if we have actually a bug or not, and to have a direction how to fix it. So for that we implemented all these visualization tools. I will show you with the video at the same time. So you can see on the right side, this is the new generated pose. And on the left side, the semi-transparent character is the previous one that we generated the last time we ran the test before the change. And we can compare them side by side. This is very helpful when there is one obvious problem, something, to see one obvious bug. Here, for example, the new character on the right was not swinging his weapon for every animation, so there is something missing that he didn't go through what he was supposed to do. So that's working well in many cases. But we have also some cases where this is not necessarily obvious what's the problem when we see the animation side by side. Here, when we see the previous pose on the left and the new pose on the right, we can see it's slightly different, but it's difficult to see exactly what's wrong. If it's actually wrong, which one is the right one, and if we have a bug. So instead, we will not focus only on the character on the right, pause it during the test, and we can switch between the new pose and the previous pose, and check with a different angle too. The new pose, the previous pose, the new pose, and even a slight difference in some of the joints would be easy to see, so we can catch it and be able to decide if we are okay with the change and if we have a bug to fix. Now, this is not only about finding the bugs, but what we also want is to be able to be efficient at fixing it. So for that, it's very important to be able to log as much information as we can. So we need to log all in text information from the pose which is generated. If we save it for the one time when we run the test, and the next time when we run it again, it's possible to compare all this information, and to know exactly at which moment one parameter in any feature will have been different, and it gives really good information about where to localize the issue and to be able to fix it. Luckily, usually in an animation system, we already have in place some way to show information on the screen to be able to debug the animation in the game. So we mostly had to log that into text file to be able to save it. So that will be just one example of all the information we generate for one frame. So that's, if we do some very simple text difference between the previous and the next one, we can see exactly which line is missing, or sometimes which parameter have a slightly different value. And yeah, we know much better what do we have to fix. Now, we had also some issue during the implementation that required a bit of iteration to get all that right. One important point to be aware is about performance. This is because we are adding a layer for the regression test on the top of the existing animation system. But this layer is really heavy because we need to do all the post-comparison, and also we need to log a lot of information, create a lot of files to the disk to be able to cache it. So this is affecting the performance of the regression test, which if they are too long to run, that can be a problem. So it's always important to be able to disable everything that will not be required for the regression test, and spend some time to make it most efficient as possible. The second problem is non-determinism. That's due to how an animation system is working. So usually when we run the animation system, it's important to run it as fast as possible. The frame needs to be as fast as possible because it will make the animation to be smoother. But this can be a problem with a regression test because it means that the same frame to generate a pose can have can make a different time to be generated. And so from one time we run the regression test, and the next time we run it, if there is any difference in this delta time during the frame, it means that it can cause some difference, some false positive, because this small difference can accumulate along the frames. And it's very important to make sure to enforce this fixed delta time for the regression test. There are also other cases where we can have determinism issues. Just for example, if one animation feature uses randomization for the parameters, this needs to be forced to be fixed also with the regression test. So it requires a bit of iteration to make sure that all those are handled properly during a regression test without affecting the logic itself. And it's important to handle all this case of false positive because it will make the regression test to be unreliable. Now, there are also other cases where where this regression test can be used beside fixing bugs. It can be used to check the effect of a quality improvement. We want to do a big change in the animation system to improve the overall quality of the animation generated poses. We can run it with a regression test and use the visualization tools that we have to be able to compare with before if we are satisfied with the change. Also, it could potentially be used by animators for testing a wide change they are doing. For example, when they need to reprocess a large amount of animation data, they can try this process on test data. And with the regression test, again, we can see a lot of information if they are satisfied with the way it's reprocessed. And as well with when using animation graphs, which are data-driven by animators, it can be useful for them to be able to run the regression test because small change in animation graph can have as well consequences in different cases in the animation content. So implementing this regression test have helped us a lot to find issues much earlier in the process. It helps us we saved a lot of time as programmers, but also for the QA team. In average, we are making around 50 50 animation features, large animation feature in a year. Maybe 25 of them are core animation code. And the time that we can save, avoiding to do bug fixing can be up to 25 or 50 days yearly. So that's a huge saving for us to be able to work on something else. And it's not only about time, but it's also about the risk. Because now we have this regression test, it means that when we do a code change, it makes the change to be much more risky. We are able to do some larger change in the code, even until very late during the development phase. And yeah, so this regression test, as you see, are quite straightforward to implement. That's a very simple thing to do. And this makes a huge difference. It makes a huge difference for us for the time, how we spend our time as programmers, and also make it can have an impact in our project, in the quality of our project. Thank you.
Thank you very much. Unfortunately, we don't have time for questions left. So thank you again.
Yeah. Thank you. If you